It is really amazing how innovation can bring clarity to the skies. So, by blending filters, mathematical models, and autoencoders, SREYA is working towards satellite images that are cleaner, lighter, and more reliable for analysis. It's a reminder that even small advances in data processing can open big doors for science and exploration. So, thank you, SREYA, for sharing such a great project with us. And thank you all for being part of PyLadies Con 2025.
So, hi, good afternoon, good morning, good evening to everyone, whoever is watching this right now, based on wherever you are across the globe. Myself, SREYA GHOSH, and today I am very delighted to present to you an algorithm proposal, which is based on a low-cost automatic compression knowledge mover technique, more directed towards satellite imaging. This is, I can say, it was like a passion project for me, which I started around 2 to 3 years back, and I was kind of slacking off on this and didn't work for it because I was facing certain roadblocks and all. And that's where I'm very much thankful to Demonstrati for joining me on this. And based on his inputs and insights, we have been working further, developing this project. And yeah, the result is what I'm going to share to you today. So, as I think everyone is aware of, satellite images are inherently very bulky. So it becomes a great hassle to actually store them and let alone denoise them, because how do you actually identify the noise from the image? So, and there's kind to be honest, the segment image is like it's very important for decision making, because if you do not know that particular calamity identifications or what happened exactly, the triggers are not being like received properly, then how to respond to them? And also like any agriculture monitoring or I know urbanization, land change detection, anything. So it becomes very important and very sensitive to work with this data. So like we already when I started with this, to that time I only know a lot of devising techniques for standing images. But like for all of them, in my eyes, I felt like either like if they're doing a very good resolution, you need to know certain factors, or else you can't, or they might be computationally expensive. So that was an objective, to at least come to a common ground where we can find a best method. Not actually best I can say right now, but a better method to actually deal with all the problems. Like as I already mentioned a few seconds earlier, images like your voices is completely dependent on your data set. Like for us, like atmospheric scattering and interference and also data transmission error with the main causes. But again, if you're working on a photonic level, quantization level, sensor, it just depends on the level you're working with. And yeah, not to forget the operational constraints with the bandwidth, storage not adequate, need of real-time processing and all. Now, so before we dive into the proposed method, let's just discuss whatever is right now in the market at a huge rate. Now, generally, if you just go through any paper or go through any software working with satellite imaging, you will see mean filtering, median filtering. This thing's very common. Now, mean filtering is an excellent technique. It's a very simple spatial averaging technique which shall work on a local neighborhood. So you have to use the 5 plus 5 kernel and with uniform weights. But it generally has a tendency to significant blurring, which is why we tried to we tested with the mean filter as well. But we didn't keep it in the result because we didn't get that good of a result, to be honest. Like I think we got around a 28.75 PSNR and a structural significance of 6.66, something like that. Now, minor fit, then comes the median filter. Median filter is a non-linear filtering technique, and it's very robust to outliers. Again, can work on 5 plus 5 kernel. Now, it does give a better edge preservation than the mean filter, but again, it is also like for us for all tests or edges whenever tending to get blurred. So it wasn't a good technique in all cases as well. Now comes the minor filtering. Minor filtering is in general a very good filtering technique which is optimal for Gaussian noises, but we need to have a prior knowledge about the model and everything, noise model and everything. So that was sometimes becomes a much of a problem if we don't have the exact credentials in mind. Now there are a few numerical techniques in the market as well, like the SVD, Fourier, Wavelet, and also there enhanced parts like a fast Fourier, fast Wavelet, enhanced SVD and all. So these are currently a um, very good ways to actually analyze the problem. They do have, if you take like singly a particular method, they do have their own particular cons. But again, the collectively they might have given a good results, which was what we explored via this project. Now, before we move forward, let's just briefly discuss about the different techniques which is available in the market right now. And like just I'm just going to explain these few methods in a bit more detail compared to the others I did before, because these are the main parts of a method, and and so that you also get an idea like what we are tackling here and why we're doing so. Now, first comes the wavelet filtering. Wavelet filtering is a like wavelet thresholding or wavelet transformations. This is currently a very like good technique for analyzing signals, especially for image processing. Majorly because when you talk about wavelet transformations, you get a lot of templates in hand, like a lot of wavelet families in hand. And based on that family, you can take, if you can match your signal accordingly, and if you can take an accurate enough wavelet family, it eases your task to a huge level. So just you have to be more careful about the wavelet families you have to gain. Like for our case, we did pick up the washing. We also experimented a bit with the Har and Wavelet and Myotoner, but we have to work with the washes. Why? Because it's an excellent well for performance technique, which I have already experienced with before. Uh, so now, whenever we talk about wavelet transformation, and just when you look at it, it just comes to you that we're taking the signal, we're converting it to the wavelet domain, and filtering the wavelet filtering it, and getting the high frequency and low frequency components. Now, based on the components, we are taking the significant features from them, then we are thresholding them, and then this thresholding is done systematically based on your image. And also, if the mode of your thresholding also depends on an image completely, like how you want to do it. We have experimented with both of them, and we're going to share the results for both the satellite image and drone image, like when you go down. And once you get your final data set, like for the final, denoised data, you can reconstruct it back and check the performance metrics. Now, coming to signal decomposition, which is again a very popular mathematical method out in the market. It is a like numerical linear algebra technique where basically an SVDs actually plays a huge great role in across the like domain. Like if I start talking about it, then it will take more time on presentation. Just so, but if for all problem, like the SVD also plays a huge role. SVD has this thing like where you can actually decompose a non-square matrix as well into components, which is the upper trigonal, lower trigonal, and a singular values, a matrix of singular values. Now, based on a singular values, we detect whether the singular values are of higher significant features or not, and based on that, we threshold them and filter it out. Now, in our case, we've also like found out the rank ratio. We have actually done our work based on the rank ratio itself. Now, what do we mean by rank ratio? Which is when generally like we make a proportion of the largest singular values to keep reconstructed image. What do I mean by that? Say you have a good image, and based on an image you can see that around 90% of your image has very significant similar values. Now, like so 10% of that, 10% of the whole image which doesn't have significant values, you can remove them, and 90% stays in your reconstructed image. So in this case you can see that your SVT rank ratio is 0.9. Similarly, you have a very noisy image where you saw that with 10% of your signal values, it can actually contribute to the final image and give you a good resolution. So in that case, see your final SVT rank ratio is 0.1. So we have experimented taking different SVT rank ratios as our input, and you get the final answers. And some of them like they did give us very nice inferences, which we discuss later, which was actually not expected. But yeah. So now coming to our actual algorithm, what we propose to do, what we did actually with it. So generally we took two type of images. One was a satellite image, another was a drone shot. Now first I'll discuss satellite image, and you can get the idea to drone shot as well. So what we did was we extract the satellite image from our data. Then we determine the drag ratio, as I mentioned. Now, after computing SVD, we made it filter through the Wiener filter to basically segregate the signal from the noise. Now, after that, we used the Gaussian Wavelet to decompose, and then based on soft and hard method, we filtered it out, and we got different results based on the different methods and threshold techniques we have used. So this is just to give you a brief view of what we did. Like we analyzed the signal values of the image, truncated them, then via minor filter we filtered out the signal, filtered the signal out from the noise, and then via threshold, via wavelet with threshold and decompose the signal. So this is how our filtering method selection works when we're thinking about non-stationary signals or like localized signal energy is present. So in that case, it's best like that's why we have to say through wavelet. Then now Vine is very good for additive noise removal, Gaussian noise as well, but we have to know the noise statistics well like before. And also SVT, like whenever we think about SVT, it's just the best dimensional reduction technique out there. This is what we get post normalization 1 to 3. So across different drag ratios, we have computed the results. So we see the best results at 0.8 SVT drag ratio. Like you can see like how good it's looking to see here. Like how similar it is to the original noise image. So like for the satellite image, satellite dataset, we did experiment in different SVT drag ratios, but we got the best optimal result for 0.8. Now you can see that we did an experiment over different families as well. But yeah, like it's evident that how like base the worksheets like giving the best results for us over the soft thresholding methods. So yeah, that depicts the success of this method for us. So here's like another method we used via drone shots. Just and briefly to say what we did because the extraction process is a bit different compared to the satellite imaging. So since it's a shot, so we first extracted the frames, different frames from it. It was around 4.4 frames we extracted from it. Now we just tested with the first, third, and fifth frame arbitrarily, and the test images were very good. So we then worked with the whole, like all the frames. Now, for the drone shots, we saw a better result at 0.9 SVT, and using base thresholding method and hard mode, you can also see the result. This was the result how it, like after the algorithm came. Like at 0.7, it's because I went home that maybe at 0.8, like just like the satellite image it would give a good result. But unfortunately it was good actually, like 9.98% it was good. But like when 9.8 was good. But at 0.7 it was better. 9.8 it was better. 0.9 was better than that. And then we got a 99.81, it's a 0.9981, which is like almost 10 to 1 and a very good value if you think that way. So result that was far with the SSI was far better compared to the mean animation filters. Now when I about to wind up, so basically just a few things I want to say before I wind up. So yeah, definitely median filter is a amazing technique and all the processors individually are amazing. But this method, this three hybrid was a very good fit for our case, as it like gave us a very good case in our SSIM and for very good high quality. Like you can see the images itself for a high quality reconstruction, high resolution at a very low storage. Now we didn't initially plan on doing the drone shots, but it just gave us more avenues to explore further. And now you might ask that so where exactly we are saying it's low cost. Now just to give you a like little idea, like when we're talking about mean is a very computationally low, very inexpensive, but medium filter at a moderate to high computation. Now when we're coming to SVD, I mean for 10 general the other three methods the hybrid we discussed, it itself like you can do it in regular CPU. Like I did it on my regular CPU. So you can do it. So first of all, you do not need any GPU or any heavy machinery to perform it. As well as your SVD computation machines, their also systems are very like cost efficient as well, cost effective if you think of the large scale level. So combining all this, we also have to, plus given all the methods in our hand, we have to come down to somewhere where it's like efficient for us as well. So And we also plan to go and make an encoder, like define an encoder which will actually automate the whole process, which we are actually working on it. It's like in a good phase, but we couldn't show you because it's still not done yet. And we have to show it by the next unit two together. So yeah, that's my 2 cents. And that's it. Like we could just show that like throughout the method like that how it's giving better results compared to the other denoising methods. No, definitely like if we might have missed certain things, but yeah, for us it did. So here's a data set like for the satellite image reference from this paper, and the drone shots were taken from drone stock. So here are references. So last but not the least, thank you all. Have a great day ahead and looking forward to more talks like this. Bye.
Hi everyone, I'm Aaron Japan, MC for this session. When we look at Earth from space, satellite images become our eyes, guiding science, policy, and discovery. But those images are often blurred by noise, hiding the very details we need most. Our speaker, SREYA GHOSH, is an astronomy enthusiast and independent researcher who collaborates on solar imaging challenges. She has been exploring a low-cost way to clean and compress satellite data, combining classic signal techniques with deep learning to make images sharper and more useful. Please welcome SREYA GHOSH with a low-cost automatic compressing and noise-removing algorithm for satellite images.